Okay, in this video I will talk about nested quantifiers, and the example that we'll use is, or that we'll start with, is this one here. Our domain is 0, plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 4, onto plus or minus infinity, otherwise known as the integers. So our domain is the integers. And our statement says, for all x, there exists a y such that x equals y plus 2. Okay. Now, what this is actually saying is that for every integer x, we can find some integer y such that x equals y plus 2. One way to go about digesting if this is true or not is to just pick some examples. Now, just picking examples doesn't exactly say whether or not it's true for all x, but it gives you an idea. Okay, so let's pick some x's. Now, with the integers, there's positive, there's 0, there's negative, so it makes sense to pick a few different ones. Let's say, start with x equals 0. Now, if x equals 0, what's a y? Does there exist some y that you can add to 2 and get 0 back? Sure. Y equals negative 2. Right? Let's think about that, right? What I'm saying here is that 0 is equal to negative 2 plus 2. So yeah, that works there. Okay. All right, let's say x is equal to, let's pick a positive number. Let's say 5. So y, in this case, is equal to 3. Okay, so it works for, let's see, it worked for 0, check. It worked for 5, check. Let's try a negative number. Let's say negative 7. Let's see, what do you have to add? So I think, let's see, we'll go with y equals negative 9. Negative 9 plus 2 is negative 7, so it worked for negative 7, check. So I'm thinking it probably is true. This is a true statement. And in fact, it is a true statement. One thing you may notice is that this equation, x equals y plus 2, this is like a line. Okay. Or this is the equation of a line, right? Okay. So for all x, there exists some y such that x is equal to y plus 2. Now, just to set the stage for things coming later, let's see, this is going to be y equals x minus 2. All right, so we're going to have a y-intercept at negative 2. Okay, and this thing is going to be, you're doing this to me again. Why are you doing this to me? A bunch of dots. Now, it would not be correct, so let me do this in red. It would not be correct to connect these dots with the line. Okay, because here our domain is just the discrete points, 0, plus or minus 1, plus or minus 2, plus or minus 3. We need the real numbers to fill in the gaps and connect the lines. So here our domain is discrete. Our domain is discrete. It has individual points. It's not continuous like the real numbers. But we'll get to that later. You don't need to know that now. I'm just sort of setting the stage for later. Okay. So now, let's look at this example with the quantifiers switched. Oops, guess I'm dealing with red still. Okay, no problem. Now, let's decide if this is true or false. Okay, so I don't know if I made this clear, but when I had for all x, there exists y, x equals y plus 2, this was true. When we have the quantifiers like this, that was true. But you'll see now if we switch the order of the quantifiers that this is actually false. So this is saying that there exists some x such that for all y plus x is equal to y plus 2. There exists some x such that for all y, all integers y, x is equal to that integer plus 2. Okay, so let's think about why this is false. Okay, so there exists some x such that for all y. Okay, so if we're talking about all integers y, then let's see, what are 2 of all of the integers? 2 of all of the integers, let's see, if we're thinking all the integers, let's do 5 and 15. I just chose 2 random integers, right? Because of this for all, we're dealing with all integers. So this is saying there exists some x such that for all possible y. If it's true for all y, then it's certainly true for 5 and 15. Right? So it's saying that there exists some x, this x here, such that x is equal to 5 plus 2 and x is equal to 15 plus 2. Let's see, 5 plus 2, that's 7. 15 plus 2, that's 17. But if x is equal to 7 and x is equal to 17, then that says that 7 is equal to x is equal to 17. That's clearly not true, right? It's clearly not true that 7 is equal to 17. This is a contradiction. So we can see that this is false. Oh, all right, let me write that in. False. Now let's look at another situation. Let's look at the original statement that we had before. For all x, there exists a y, but with a different domain. Oh, let's actually go like this. Okay, so now our domain is the natural numbers. The counting numbers, 0, 1, 2, 3, 4, 5, 6, 7, on to infinity. And this is saying that, again, that no matter what natural number you pick, because we've changed our domain now, right? Remember that? We've changed our domain here. Big important part is we've changed the domain. This is saying that no matter which natural number you pick, there's some other natural number that you can pick, y, such that x is equal to y plus 2. But this isn't true for x equals 0. So let's consider x equals 0. If x is equal to 0, right, that's saying that 0 is equal to y plus 2. Solving for y, we get that y equals negative 2. So, but y equals negative 2 is not a natural number, right? Do you see that? There's no negative 2 up here. So the order of the quantifiers makes a difference, and what your domain is makes a difference. It's been fun.